This is track 1, so we're going to be looking at innovations in teaching and the challenges of the current state. And I'm very pleased that we have Louise Dawe joining us, who's going to be speaking about remote instruction. And I will just turn it right over to you, Louise.
Thank you for the introduction, Carmen. So good afternoon, everyone. My name is Louise Dawe. I'm an associate professor of chemistry and biochemistry at Wilfrid Laurier University, which is in Waterloo, Ontario, Canada. I'm going to speak with you today about remote instruction as an opportunity for students to engage with structure. I'd like to thank Catherine Kantarja for the excellent talk she gave right before the lunch break, which I think surveyed some very higher level and broad topics with respect to some of the opportunities we have for technology and remote instruction. I'll tell you that at my own university, I've been leading a community of practice in large classroom teaching in a remote environment leading into our fall term, which at my university starts on September 10th. And at this point in time, the members of my community are very much focused on, at this point in time, what are the practical things that we can do, that we can implement in the short amount of time that we have left. And so today I'm going to give you 2 examples from my own teaching that I think are readily adaptable to remote instruction, as well as some of the practical tips and tricks that came out of my teaching and organizing the remote Canadian chemical crystallography workshop that took place last May. Okay, so in getting started here, I do want to first acknowledge that some of the origins for the ideas in this talk actually come with the people on this slide who've provided me with information over the years about some of the global schools for learning crystallography that take place that I haven't been to all of them. And so I want to give a shout out and thank you to everyone who's been involved in teaching the next generation of structural scientists and for being such great mentors to me as well. Okay, so I'm going to start with a little bit of undergraduate curriculum. And so I'm going to point out that according to the American Chemical Society, their accreditation guidelines require that accredited institutions have access to NMR facilities, access to 4 of the following types of characterization. Nowhere is X-ray crystallography explicitly mentioned on this list. And if you have you go in for a deep dive and looking at the inorganic and the organic chemistry accreditation curriculum requirements, you can sort of extrapolate from the organic chemistry side of things that purification methods are mentioned, and recrystallization is a purification method. Characterization methods, well, X-ray diffraction certainly counts as one of those. So I'm north of the USA, and in Canada, it's our Canadian Society for Chemistry that also regulates accreditation. And it's a little bit less prescriptive than what the American Chemical Society requires of its accreditation programs, but there is still an examination of departmental and financial support, lab hours and access to equipment, and in particular there's an emphasis on access to library resources. Okay, so the Canadian Society for Chemistry Accreditation actually states that it shall neither prescribe a detailed curriculum beyond the minimum requirements detailed in this accreditation document, nor does it require uniformity among programs, which means that from one university to another, there actually is a bit of diversity in terms of what you might see in first semester versus second semester general chemistry, or what you might see in first versus second versus third year inorganic chemistry, for example. And so I'm going to draw from 3 examples of courses that I've actually taught at 2 different universities. And so these are simply the calendar descriptions. And as we might expect from our calendar descriptions, these are very short descriptions of what a student might expect when taking these courses. But within all of these short descriptions, I, with my eye to small molecule X-ray crystallography, see opportunities for bringing structure into the curriculum. So if I'm seeing these opportunities to talk about structure and crystallography, then how exactly is it that we should go about teaching this? And so there was a 2014 paper published in PNAS. I think it's possible that part of my screen is being cut off. I'm sorry. So if you're not seeing the full references, if you email me after, and I'll be happy to provide you with any of the slides that I'm showing. But this meta-analysis actually indicated that, in terms of achieving statistically significant impact on student learning, that active learning activities are the activities that we would like to be using in our classrooms. And so specifically what this article pointed to is that in the 225 studies that were examined, looking at the impact of active learning versus traditional lecture-based teaching, which is what I'm doing right now, that what it was found that students that were engaged in active learning activities scored 0.47 standard deviations higher on evaluations. They had average exam scores that were 6% higher, and I think that is what is particularly relevant to us moving into these remote teaching environments where student attrition is a serious concern. It did show that failure rate in these courses was 1.5 times less, and so it does give us a bit of hope about what are some methods that we could use to retain students in our courses this fall. Okay, so a couple of examples then of some active learning crystallography activities that are amenable to being done from home. So the first example I want to point out comes from a third-year spectroscopy course that I taught, but I also first piloted this activity many years ago with high school students that were participating in SHAD. So SHAD is a science and entrepreneurship camp that takes place across Canada at multiple different university campuses. Really exceptional. High school students spend a month engaging in lectures, workshops, and coming up with a science or engineering product that is marketable at the end. And so I did a workshop with these students, timed to coincide with the IUPAC technical report on defining the hydrogen bond and Desiraju's paper on a bond by any other name. And so tying this redefinition of a traditional hydrogen bond being the result of a highly electronegative atom directly bonded to hydrogen interacting with another highly electronegative atom. We actually looked at several examples that were from this paper on the applications of the Cambridge Structural Database. And so I curated examples from the teaching subset so that students would be able to ask themselves the following questions. What is the donor hydrogen acceptor bond angle in these examples? Does it tend towards linearity? Is it consistent with the new definition of a hydrogen bond? Does it contradict the old definition of a hydrogen bond? And so many of the examples that we looked at were still traditional hydrogen bonding, looking at amines, looking at carboxylic acid dimers. But the great thing about the Cambridge Structural Database teaching subset is that once students get loose inside that subset, I find that they seldom stick to the prescribed suggested examples, and they go on explorations. And so I have to say, when I did this workshop with the students from SHAD in particular, it was exhilarating to see their enthusiasm for looking at all the different structures. And of course, they are all slightly entrepreneurially minded, and so many of them were then thinking about, well, how would I be able to, put these molecules in devices, and how could I market this? And then they came across this particular example and sort of flipped everything on its head for me. So this is 2-butene, and it is co-crystallized with hydrogen chloride. And they asked me, is this an example of a hydrogen bond? And so I did what I do when I teach. I turned it back on them and asked them, well, ask yourselves the questions. What's the bond angle? Does it tend towards linearity? Does it agree with our traditional definition? Does it contradict the traditional definition? And so I have to say that this type of exploration can readily be adapted to the situations that we are facing in the fall. And so the next example I'd like to present you with is one from an inorganic chemistry class that I've taught. And in 2014 in particular, this was difficult. And in fact, this is difficult right now because I've hidden everyone in an attempt not to be distracted. but you know, sometimes even in person, it's like everyone is hidden when you're in a class and people's faces are all blank stares. And so that semester in particular, I was feeling like I wasn't connecting with my students. And so I asked our Center for Teaching Innovation and Excellence to come in to conduct a mid-semester survey so that I could find out, are students struggling with this course? What could I be doing to better engage them? And one of the questions that was part of the survey was, what, if anything, would you change about the PowerPoint slides? Please be specific. And one student commented, too many words, cut down on the words, which is what I think this presentation may be a bit like. The other one was, the only suggestion is for more examples or worked out problems, since molecules and models are hard to visualize. And this is absolutely true. So this feedback coincided with when we moved on to the second unit in this particular course, which was looking at metal complexes. And so, you know, if we look at the learning outcomes for this particular unit, the students were expected to determine ligand denticity, to use IUPAC nomenclature to name metal complexes, to recognize and describe common coordination numbers and bonding geometries, apply crystal field and ligand field theory to predict low spin versus high spin metal configurations, and to determine magnetic moments for simple metal complexes. Okay, so when we think about when we are teaching and assessing, our assessments should align with our learning outcomes. And so I had planned to engage the students in an assessment whereby they would be able to demonstrate to me their mastery of these outcomes. And so the way I went about doing this is that I went through the CSD looking at that time for private communications that contained copper. And so the idea was that each of the students was provided with their own crystal information file from an unpublished structure, so they wouldn't be able to go to the literature to get all the answers. And then they actually engaged in preparing their own Acta Christi style report. So now this would be an IUCR data publication. Regardless, you can still use PubLCIF, and the templates for this type of communication are free, readily available, and once you obtain the CIF as a private communication or now as a CSD communication, you can readily import it and then start answering the questions about what's contained in this particular structure. Now, I selected copper as what I did, and I thought today it would be fun just to have a look to see how many structures could you pick from to do this activity. And a conquest search this morning showed that there are currently 2,226 copper-containing CSD communications that are readily available for anyone who wants to engage in this kind of activity. Okay, so in addition to providing the students with the assignment, I also provided them with the grading rubric. So I always provide the students with the rubric ahead of time so that they'll know what it is that I am expecting for demonstration of mastery. Further to that, these are second year inorganic chemistry students. I'm asking them to prepare figures using mercury, to use PubLCIF, to open a CIF file. This is a lot of stuff that they don't know. So I prepared a full software tutorial for them. We also had an in-class tutorial where we all used the same CIF file and actually went through this activity before they were assigned their own individual structures. And if we look to the rubric that was provided for each of them, you'll notice that there were marks associated with the title, author, affiliation, keywords, but in the structural commentary, which is still something, structural description, that you would still include if you were going to do an IUCR rapid data communication, the expectations were that the coordination number will be discussed. It should include the coordination number of the metal, denticity of the ligands, coordination geometry supported by bond distances, angles, Addison's tau value, point group symmetry. Reference should be made to the figures. Oxidation state of the metal should be identified. Implications for d orbital occupancy based on Jahn-Teller distortions for copper 2+ complexes, as well as comparisons to similar complexes, which I also expected them to identify. So over the years, I've had a few people that have asked me, how'd this turn out? Because even with this tutorial and these clear instructions, how how did students actually do on this assignment? Well, I will tell you that some of them were quite disappointed by their marks, but I actually provided them the opportunity to include my feedback. So for every single one of these items in the rubric, along with their mark, I actually included comments on each of these points that I had outlined that I was expecting to find. And for any student who wanted to revise and resubmit, which is something we were quite familiar with, their final grade would actually be weighted with the mark scale to be 35% of their original grade and 65% based on their revised manuscript. Okay, so those are two practical suggestions that I have for activities that could be implemented this year. I also sort of wanted to shift gears because I thus far spoken about a couple of undergraduate activities, but what about students that are graduating from these accredited programs, whereby keen faculty members that love structure may be incorporating this into their courses, but it's not required. So we see a lot of graduate students that are coming to us, and they would greatly benefit from additional expertise in crystallography, but resources to develop these skills in our graduate students might be limited by facility access, expert availability, budgetary requirements. And so this does sort of point to the practical aspects of offering targeted local or regional workshops that would attract a larger number of students and possibly a larger number of expert instructors. So even in similarly themed workshops, we see that the diversity of experiences that attendees have, there are logistical aspects of organizing that can vary, and exactly what do students get out of it varies as well. So I do want to point out that there are a large number of opportunities for people to engage in these types of activities globally. A special note to the IUCR Open Labs initiatives that sort of started coinciding with 2014 as the International Year of Crystallography, and that have really been instrumental in bringing crystallography to areas in which this is still identified as being an emerging area of science. I'm going to speak shortly just about my own experiences with the Canadian Chemical Crystallography Workshop. So between 2012 and 2015, I taught at the American Crystallographic Association summer course. In 2016, I started teaching at the Canadian Chemical Crystallography Workshop. And in 2019, I took over as the organizer of this workshop. So it's a 4-day course. I used to have a very flexible agenda. I'm not such a flexible person though, so the agenda's gotten a little bit more strict in the last 2 years. We cap enrollment at 30 people, and we normally have trainees that come from across Canada and various international locations. And I will tell you that my clear goal for this is not to develop crystallographers, but to develop critical consumers of X-ray data. So I want people to leave feeling that they're empowered to question the literature, feeling that they can, include looking at the CIF file as part of their review if they're asked to review an article. And so we've actually gotten great response over the year. We've actually we've gotten great response over the years. A couple of our attendees are actually 2-time attendees because you sometimes don't know what you don't know until you know a little bit. And so several of our attendees learn a bit about crystallography, and then realize what a great opportunity this is to engage with experts and to get their questions answered. So they come back a second time. Sebastien actually defended his PhD there. He just got official word that it was successful this week. And so if he does want to come back and help organize, we will welcome him with open arms. So this was the curriculum that we executed in May of 2020. We had originally been scheduled to have a local workshop in Winnipeg, but with the pandemic, my instructors were actually very enthusiastic to convert to a remote format. And so we actually had one-on-one time using breakout rooms in Zoom first thing in the morning each day. We had lectures in later morning, and then we had workshops and tutorials in the afternoons. I will tell you that we had excellent support from our sponsors. We had faculty instructors that came from Brooker, from the CCD, and from Rigaku. And I just want to tell you that we actually did have 24 students and 11 instructors that joined us from across Canada, from BC through to Newfoundland. We actually had an attendee from the US as well. I just want to now speak to a couple of logistical aspects. The first one was that we did not have prior consent to record the lectures. And so we actually did get a few requests afterwards from non-attendees to access the lectures. And so if you're thinking about organizing something like this, prior consent and how will you deal with requests from outsiders to access your material is something to consider. We conducted an anonymous post-workshop survey with 24 respondents. 90% reported the quality of the instruction, background information, content, use of OLX2, furthering of knowledge was good, very good, or excellent. And we offered free-form feedback. And I will tell you the two biggest things that actually came from the free-form feedback was suggestions that in an online environment, it's very easy to go too fast because we don't know how students are keeping up with us because you can't look over their shoulders. The other thing was that we didn't think ahead of time to recommend that maybe they should have access to a second monitor, because if you're trying to teach someone by speaking with them on Zoom while hoping that they're simultaneously engaging in this activity, it's hard for them if they're switching between monitors. So those are a couple of the big logistical aspects I took from that. There are a lot of other logistical aspects that people should consider if they're thinking to organize these types of workshops. And certainly anyone who would like to discuss this with me afterwards, we could delve into a lot of these different aspects. I will also say that I've got a list of other educational resources, as well as if people want to attend conferences, where are there opportunities to secure funding. And again, if you'd like these, because I know lists of references on slides is not the most useful thing, just email me, tweet at me. I'll be happy to send you these slides that you can, peruse the various links. So with that said, I want to give a big thank you to all of the instructors that stuck with us for the Canadian Chemical Crystallography workshop this year as we went into a remote environment. And I do just want to give a shout out to two of my colleagues in Canada who have been running a global inorganic discussion series ever since the pandemic started. They've just published a perspective article in the Canadian Journal of Chemistry, and they've got other additional insights, perspectives, and reflections that are quite useful to anyone who is considering moving into an online and remote environment. So with that, I want to say thank you very much for giving me the opportunity to share this with you today.